Welcome to this next lecture on fundamentals of acoustics. In the next few lectures we will look at measures of sound. Of sound level. Okay. That is how to measure sound and how to give a number to the level, how to know if one sound level is louder than the other, if it is louder by how much and what is the frequency content. That is the topic in the next few lectures. Okay. So now let us talk of a signal, okay, a signal, a sound signal, the sound signal. If I let us say utter the word acoustics, okay, I have said acoustics, then maybe the pressure as a function of time and time here, maybe the signal looks like this, acoustics. Okay. So it goes both positive and negative, right, because when I am saying something I am also breathing in and out, and the organ of speech is doing many things. So in order to produce a sound like acoustics, the oscillations have to be there in air. That is how it may look like. Now if I utter, let us say, the word fundamentals, it is a little longer, I do not know how much, it may look like this. Okay. Now in the average sense of average sense, over the entire time, over the entire time, which sound is louder? Which sound is louder? Okay. Or which sound has more power, or which signal has more power? Okay. Or what is a number? What is a number that indicates that particular sound and its feature? Okay. Now just hypothetically, suppose we say we take the mean value, the mean value of the signal, mean value of the sound signal. Okay. Then if we take the mean of this or the mean of this, it may average out to 0, because it has positive parts and negative parts. Positive parts and negative parts. So it may average out to 0. So mean is not a good measure. Mean is not a good measure. Okay. Now what we say is that the square of the signal is a measure of the power, is a measure of signal power. Okay. So if we square any of these signals, then it will remain on one side. Okay, it will remain positive and may change the amplitude a little bit, etc. Okay. So there is no negative part to the signal. There is no negative part to the signal. It is just positive. Whatever. Okay. Now, so now we have a signal and we have squared the signal. Okay. We still want to give a single number. Okay. An event occurred, somebody said something, or one speaker came, said something, and the next speaker came and said something. So now we want to measure the loudness, who is louder. So we square the signal and then we take a mean of the signal. That means we, over the time 0 to t, p square of t dt. Okay. So this is a mean of the square of the signal, mean of square of the signal. It's a single number. It's a single number. Okay. Then what we do is, in order to bring it back to the pressure unit, we take a square root. We take a square root. So we square the signal, we take a mean of the signal, we take a root of that value. Okay. So this is the RMS value, root mean square value. So root mean square implies root of mean of the squared value, squared signal. Okay. So you go backwards, you square the signal, you take a mean, you take a square root. Okay, root of mean of squared signal, that is RMS value. So RMS value is one reasonable measure of the strength of the signal. Strength of signal. Okay. Now that's one aspect we have arrived at. RMS, we like RMS. Okay. The other aspect is that sound levels hugely vary. Sound levels from situation to situation. Okay. To situation. Very heavily. Okay. So that means what for example, if we, let's say, what shall we say, we talk of a rocket, Saturn rocket. Okay, it may generate a power level of 180 decibels and a power of 10 to the power 6 watts, whereas a normal voice, okay, maybe shouting, can generate about 90 decibels of power level. We will discuss this, and that could be about 0.01 watts. You see the huge difference in raw power. Okay, this is the same in terms of, right, in terms of pascals also. Okay, if we say, we talk of a jet engine, okay, let's say about a certain distance away, let's say 10 meters away, it could generate about 600 pascals. Okay, whereas a normal conversation, a meter away, you have a friend sitting at a meter, 1 meter away, that could generate about 10 to the power minus 3 pascals. Okay, so that's a huge difference, in levels. So now if you stick with these numbers, then on a single plot, if you are going to do a plotting, then 600 pascals may be somewhere there, and 10 to the power minus 3 pascals will be somewhere here. Okay, or even the same source in raw pascals may have a huge variation from its loudness to quietness. Okay, so when it's loud, it could be a certain number of pascals, it's quiet, it's certain other number of pascals, and this is huge, so the details will be lost in raw pascals. Okay, in linear units, if we represent the sound levels, then the details will be lost. It's like one of them is a Eiffel Tower, the other is a hut or something. So one end of the detail will be lost. So that is the reason we use the decibel scale. Which compresses the differences. So that we can have a graph on the same axis. We can show levels on the same figure. Okay, so now the second, so one first was we want to get into root mean square, the next is we want the decibel scale. Okay, so what are the measures of sound? Okay, what are the measures of sound? In the decibel scale, measures of sound, okay, so one is called the sound pressure level. Okay, SPL, this is given the symbol LP. LP means sound pressure level. What is it? It is in decibels. So you have LP decibels given by 10 into log to the base 10 P square, root means square value, by P square reference. Okay. So what is this P square reference? P square reference or P reference, let me say P reference is 20 micropascals. Okay. So that means what? If P square RMS happens to be P square reference, then this ratio is 1 and that is 0. So P reference is some kind of a threshold of hearing. Threshold of hearing. Okay. Now this is a very subjective thing. So this was arrived at after talking to people, bringing in subjects. Okay, bringing in subjects and asking them questions. It was figured out that this value of P reference 20 micropascals is somewhat the threshold of hearing for human beings. Okay, so this is one measure of sound. This is a point measure. Okay, at one point in space you put a microphone. That microphone will pick up some signal P of t. From P of t we convert it to PRMS or PRMS, and that RMS is used in here to compute decibels. So this is a point measure. At a single point you measure. Okay. Now the next measure, okay, is called sound intensity level. Okay, SIL, given by the symbol LI. LI means sound intensity level. Okay. So now what is this sound intensity level? It is given by 10 log to the base 10 intensity by intensity reference. Okay. So where in dB, this is dB. Okay. So this also becomes LIDB. I think LIDB. Okay. Yeah, LIDB, capital IDB. Okay. So now this is also a point measure. This is also a point measure. Okay. It is given through intensity. And what is intensity? Intensity is 1/2 the real part, or the time averaged intensity is 1/2 the real part of P into V conjugate, pressure into V conjugate, Okay, v here is velocity, which is a vector. Okay, so it is a vectorial quantity. Intensity is a vectorial quantity, sound intensity, vectorial. Okay, so at a point you have a pressure and a certain velocity. Okay, so when you compute this, this is the intensity in that direction. Okay, now how do you compute or measure? How to measure? We are talking measurements, so how to measure intensity? In experiment or in in experiment. So the way it is measured is that you need pressure and you need particle velocity. You need both to get this quantity. Okay. So in experiment, again our friend Euler equation comes to our help, which says that del P by del X is equal to minus j omega rho into velocity. Okay, or let me say del P dot n here. Del P dot n is V dot n. Okay, so the directional derivative of pressure is the velocity dotted in that direction and minus j omega rho. Okay, so in 1D, like for example 1D, this ends up as del P by del X is equal to minus j omega rho V, the magnitude of velocity in the x direction. Okay, Vx, let us call it. Okay, so now the gradient of pressure, so that means what? The gradient of pressure, is proportional to velocity, proportional to particle velocity. Okay, but if you want to measure gradient, that means you need to measure at a certain location and you need to measure at another nearby location. Okay, take the difference and divide by, okay, difference and divide by distance. So you need two microphones. You need two microphones. So typically what they do, they have a 2 microphone setup. It's called a 2 microphone intensity method. Okay, so you have a microphone like this which faces another microphone, okay, at a distance. These are standardized distances. One of them I think is 12 millimeter, the other probably is 50 millimeter, etc. So you can adjust them to a standard distance. So this is one mic and this is one mic. So this measures P1, this measures P2. Okay, so average pressure P is P1 plus P2 by 2, and if you want, the gradient can be found by P2 minus P1 by the distance delta, that is proportional, that is converted, okay, proportional to particle velocity. Okay, so there is a 2 microphone intensity probe, a system which comes with a hardware and a software, and it automatically gives you the intensity in decibels. It does the entire calculation and it gives you the intensity in decibels. Okay. So, the particle velocity in this case is aligned with the probe direction. So, intensity is in that direction. Okay. Now, what typically is done is that if a system is making sound, if a source is making sound, let us say a source is making sound, a grid is constructed. There is a mesh either of thin wires or ropes that is constructed, okay, and there are further divisions made based on the engineer's idea of the frequency content. Okay. If the frequency content is low, these grids can be large. If the frequency content is high, you have to make it small because you have to capture the variations. Okay. And then let us say we have broken that mesh into small areas. Now we take our probe, this probe here, we take this probe, then we set it up here so that one microphone is on the outside and the other on the inside, okay, and then we scan this area slowly. We start the machine, starts to measure, okay, and then you scan this area. Typically you scan in a very systematic manner, and during that time the intensity is measured and averaged also. So you get the average intensity in decibels. Okay, and that can be taken as a measure at the center of the region. Okay, this is the second number that we have, and the I reference is 10 to the power minus 12 watts per meter square. Okay, so that's the reference. Now the third of course is the sound power level. Given the symbol LW, okay, it is an area measure. It's an area measure. Okay, and what is the formula for it? LW in decibels is given by 10 log to the base 10 power by power reference, where the power reference is 10 to the power minus 12 watts. Okay. Now we had said that so that's three standard measures. Okay, there are a few others, but these are the most common measures. Okay. Now how are the references chosen? How are the references chosen? Okay. Now I have said repeatedly that it is always advisable to measure sound intensity in the far field. Okay. okay, because in the near field of the source, there will be near field effects, so that the particle velocity is out of phase, largely out of phase with pressure. Okay. There is an in phase component, which is responsible for power. Okay. But in the near field this dominates. So you have some source and you are in the near field, and near field is just very highly active, and high, many wave numbers, many oscillations are happening over there. Now if you try to measure intensity where you will average, just as the machine averages, you average, then this averaging is very sensitive to the levels, dominant levels. So the out of phase velocity component may dominate, whereas the in phase component will be buried. Okay. And if you do not average properly, the out of phase component may not get averaged out. Okay. So you will be in error. If you go and measure intensity or try to measure sound intensity in the near field of a source, the likelihood to be erroneous. So you have to be in the far field. Okay. Far field we say anywhere between 5 lambda to let us say 10 lambda. Beyond that, if you go, you will be in the far field. Okay. Of the smallest wavelength, okay, smallest frequency, sorry, of the smallest frequency. Hence the largest wavelength that is contained in the frequencies generated by the source. Okay. Now in the industry, in an industry, you may not have the choice to be in the far field. No choice to be in the far field. Okay. So you could have a machine, and that machine is at one corner of a room. Okay. And then you have to measure, the wall is very close by, this wall is very close by, and the room itself may be very small, etc., and you can't move the machine. So you have to take measurement in that situation. So then you can't do anything but follow ISO standards. There are many ISO standards for measuring sound. Okay. If you have a room with two corners, or if the machine is close to a wall, how to measure. If the machine is close to two walls, how to measure, how many points to measure, all these are set up. So if people follow these standards, then the reporting will be standard. Okay. But it may not be in the far field, but you have done a standard job so that you can compare with another machine in another place and so forth. Okay. But suppose you have a choice, to be in the far field. Be in the far field. Okay. So now let us see, the averaged intensity is given by 1/2 the real part of P V conjugate. Okay. In the far field, we will take it as P by rho C, plane wave relationship. Okay. So that I have 1/2 the real part of P into P conjugate by rho C, which is 1/2 magnitude P square by rho C, or magnitude P by root 2 squared into 1 by rho C is equal to P square RMS by rho C. Okay, if I have, so we'll see this a little bit later. From peak pressure to RMS in a single sinusoid is, a peak is P, RMS is P by root 2. Okay, so that's why the averaged intensity in the far field is given by P square RMS by rho C. So now let us look at this. We have let's say LP given by 10 log to the base 10 P square RMS by P square reference, and Li given by 10 log to the base 10 P square RMS by rho C into intensity reference. Okay. Now based on this we will relate P square reference to intensity reference. This we will see in the next class. I stop this lecture here. Thank you.